3D surface modeling for Fajr verification. Jakarta has just officially set a lockdown in anticipation of the COVID-19 outbreak starting April 10, 2020. Despite the fact the introduction of social distancing campaign 2 weeks earlier. Therefore, by the time of the official announcement, the congested traffic, one of the primary cause of air pollution in Jakarta and surrounding areas, have been reduced significantly. ISRN anticipates the low air pollution by taking remote sensing data for the Fajr study since April 6, 2020. Observation of this data ends on April 23, the day before Ramadan fasting. We are now preparing a complete report for the 18-day Fajr. In the meantime, in this video, we are presenting a new study entitled 3D Surface Modeling for Fajr Verification. We are from the Islamic Science Research Network, ISRN-UHAMKA, Jakarta, Indonesia. Remote sensing data during the lockdown. During the national lockdown due to the COVID-19 pandemic, ISRN is collecting remote sensing data from April 6 to April 23, 2020. During the time, air pollution is considered at the lowest as pollution contributing industries closed down. 90% of the traffic in congested Jakarta is in severe restriction. Environmentally, this condition only occurs might be only 1 in 500 to 600 years. ISRN used to rely on the use of a non-imaging sensor, e.g., the sky quality meter, for the collection of the Fajr data heavily. However, we realized that people, in general, do not quite understand this type of data. SQM records an aggregated value of the sky brightness data sampled by its sensor that forms an upside-down cone with the apex angle of 20 degrees. Therefore, if someone somehow manipulated the data processing, people might not even be aware because the corresponding image is not available for comparison. Owing to these significant drawbacks, we therefore are trying to switch to using imaging sensors instead. As such, we now have a variety of choices. It ranges from a rather expensive and high resolution of DSLR camera, a panoramic camera with a fisheye lens that is capable of capturing a half hemisphere. Most importantly, though, it also includes gadget cameras that become a piece of the necessary equipment on any mobile phone now. ISRN is now able to collaborate with anyone willing to give contribution to the development of the global twilight pattern. The most significant benefit of using an imaging sensor is that it has very similar characteristics to human eyes. It resembles most the way the Prophet and his companions undertook to determine the Fajr some 1,400 years ago. The only difference which even gives invaluable advantages is it is capable of recording at any time we want. It is unavailable when we use the naked eye to perceive the presence of the Fajr. Remotely sensed data from a gadget camera. In line with the principle of crowdsourcing data collection, almost everyone now owns a mobile phone equipped with a gadget camera. Worldwide collaboration will almost all Muslims across the world are therefore possible. We encourage as many Muslims now to contribute to collecting the remote sensing data for the compilation of the global twilight pattern. Besides, supporting applications are available at meager costs or even free of charge in the public domain. In our report now, we demonstrate the use of LapSID application installed on a Vivo gadget camera. We acquired the digital image at a temporal resolution of 10 seconds on April 7, 2020, from 4 hours 38 minutes and 34 seconds to 5 hours 44 minutes and 24 seconds and an interval of 10 seconds. In total, there are 396 image frames. Each frame consists of 1,920 columns and 1,080 rows, giving a total number of pixels of more than 2 million pixels in a frame. These two figures on the right show the pixel distribution of image ID 180 and 256 respectively. The camera automatically recorded image 180 at 5 hours, 8 minutes and 24 seconds. Simple image processing software calculates the distribution of the pixel population in the form of the histogram, as shown in this figure. The number of the black pixel, or Grey-Label 0, is close to 1.7 million, while the number of Grey-Label 20 is about 3,000. Of course, we can hardly see the latter in the figure. Simple calculation further gives the standard deviation of 5.07 Grey-Label for the image 180. The standard deviation is a measure of the spread of the pixel population. Furthermore, the camera recorded image 256 at 5 hours, 21 minutes, and 4 seconds. This figure shows its corresponding histogram. The number of black pixels now decreases dramatically from 1.7 million to 85,000. Consequently, the number of pixels of Grey-Label 20, which is a brighter pixel, now increases from 3,000 to about 64,000. So does the number of other brighter pixels as the total number of pixels in an image remains unchanged. Again, a simple calculation gives the standard deviation of 24.90 Grey-Label for image 256. Therefore, the brighter the sky, the larger the standard deviation. It is similar to the value of the magnitude per square arc second recorded by the sky quality meter. This slide shows the timeline plot of the standard deviation change from 5 hours, 8 minutes, and 24 seconds to 5 hours, 27 minutes, and 4 seconds. The official Fajr occurs at 4 hours, 34 minutes, and 31 seconds at the sun depression angle of -20 degrees. However, the mathematical model applied to the plot proves that the real Fajr occurs at 5 hours, 12 minutes, and 44 seconds, or the sun depression angle of -10.64 degrees. 3D surface modeling for the verification of the presence of the Fajr. The following slides demonstrate that the development of the number of brighter pixels in the form of 3D surface modeling proves that the Fajr has not occurred before 5 hours, 12 minutes, and 44 seconds. Let us have a look at the 3D surface model of image 1 taken at 4 hours, 38 minutes, and 34 seconds. At this time, the sun was at its sun depression angle of -19.03 degrees as it only 4 minutes after the official Fajr at 4 hours, 34 minutes, and 31 seconds. At this point, it is 34 minutes and 10 seconds away from the real Fajr at 5 hours, 12 minutes, and 44 seconds, and 1 hour, 14 minutes, and 22 seconds from the sunrise. Everything is pitch black to show that the Fajr has not occurred yet. In the next slide, we jump to image 110 taken at 4 hours, 56 minutes, and 44 seconds, or about 16 minutes before the real Fajr at 5 hours, 12 minutes, and 44 seconds. It is some 56 minutes and 12 seconds away from the sunrise at 5 hours, 52 minutes, and 56 seconds. At this point, the sun was at a dip of -15.57 degrees. We cannot differentiate this 3D surface model from the previous one for image 1, even though the time had lapsed more than 18 minutes. It is therefore impossible that the Fajr occurred somewhere between image 1 and image 110. Neither did we can differentiate the 3D surface model for image 122 taken at 4 hours, 58 minutes, and 34 seconds when the sun was at the dip of -14.12 degrees. Image 134 taken at 5 hours, 0 minutes, and 44 seconds when the sun was at the dip of -13.59 degrees. Image 146 taken at 5 hours, 2 minutes, and 44 seconds when the sun was at the dip of -13.10 degrees. We can continue until image 194 taken at 5 hours, 10 minutes, and 44 seconds when the sun was at the dip of minus 11.13 degrees. Therefore, it is improbable that the real Fajr occurred between image 1 and image 194. In the meantime, the mathematical model has been able to estimate that the real Fajr occurred on image 206 taken at 5 hours, 12 minutes, and 44 seconds. It was when the sun was at its depression angle of minus 10.64 degrees. Consequently, the significant differences in the 3D surface model also occur between image 206 at 5 hours, 12 minutes, and 44 seconds, and the following images. The significant change in the 3D surface model for image 218 taken at 5 hours, 14 minutes, and 44 seconds. It was only 2 minutes after the real Fajr. The sun was at the dip of minus 10.15 degrees, or some 38 minutes from the sunrise. The change in the 3D surface model is the consequence of the presence of the number of brighter pixels. It is due to the nearing sun towards the local horizon. The twilight is getting brighter exponentially. For image 230 taken at 5 hours, 16 minutes, and 44 seconds, or 4 minutes after the real Fajr, the sun was at the dip of minus 9.66 degrees, or some 36 minutes from the sunrise. For image 242 taken at 5 hours, 18 minutes, and 44 seconds, or 6 minutes after real Fajr, the sun was at the dip of minus 9.16 degrees, or some 34 minutes from the sunrise. We can go further until image 302 taken at 5 hours, 28 minutes, and 44 seconds or 16 minutes after real Fajr. The sun was at the dip of minus 6.70 degrees, or some 24 minutes away from the sunrise. Conclusion. The Fajr had not occurred when the official call for prayer at 4 hours, 34 minutes, and 31 seconds or at sun depression angle of minus 20 degrees on April 17, 2020. Instead, the real Fajr occurred at 5 hours, 12 minutes, and 44 seconds when the sun was at a depression angle of minus 10.64 degrees. The 3D surface modeling is instrumental in verifying the presence of the real Fajr. It is impossible to use the SQM data to do such verification. We encourage Muslims all over the world to collect the remote sensing data of the Fajr at their localities. ISRN will be more than happy to assist any technicality in collecting and processing the data. It is free of charge. Almost everyone now owns a gadget camera. Besides, a free application for image data acquisition is downloadable free of charge from the Play Store. Take images from the time of the official Fajr at a local time until about 10 minutes before the sunrise. Use a temporal resolution of 10 seconds. Any contribution will be acknowledged and highly appreciated. Assalamu alaikum wa rahmatullahi wa barakatuh.